Okay, the title of this lesson is section 9-4 in your workbooks, and it's transforming exponential expressions. And so I have the standards listed here for you, but the main question that we're going to try to answer today is how can we transform and interpret exponentials? How can we compare which is the better deal, which is a better interest rate? So we're going to look at that. Okay, so to discuss this, I want to begin by showing you this little video clip.
When saving money for a car, you may want to open a savings account with a local bank. Because banks offer different interest rates, it's a good idea to compare the rates before making a decision, so your money can earn the most interest. Suppose you receive offers from two different banks. If you open a savings account with Savewell Bank, your interest rate will be 0.15%, compounded monthly. Second local bank offers 2% interest, compounded annually. While 2% interest sounds better than 0.15% interest, the comparison isn't quite that simple. Because the banks compound interest at different time frames, it's a little harder to compare the benefits. Which bank would be the better choice?
So looking at this, we know that the one is compounded monthly.
Saving money for
That
a car
means that it's being compounded 12 times a year, whereas the other one is only being compounded once a year. So compounding your money 12 times, that means they're compounding it, they're giving you a little bit more, and then they're compounding it again, and they're giving you compound interest on what you have plus what they gave you the last time. So you think about that happening 12 times over a year, you're gaining a lot of money quickly, whereas with the other one, you were just looking at it, it's just happening once a year. So in order to be able to compare these two things, we need to have them it'd be like trying to compare inches to centimeters. You know, you can't compare inches to centimeters unless you first convert the inches into centimeters and then compare centimeters to centimeters. So that's kind of like the big picture here. That's what we're trying to do. We have something compounded monthly and something compounded yearly, and we want to try to look at what they would both come out as compounded monthly in order to then make the comparison at what would be the better deal. So it says write a function to represent the amount A that would be earned after T years with the second local bank. Then write an equivalent function that represents the monthly compounding. So for convenience, we're just going to let the initial amount of money that you deposit into the bank account be $1. We all know that that's kind of ridiculous. Put $1 in the bank, but not really ridiculous, but if that's all you have, that's all you have. But that's where we're going to begin, is by looking at just that $1 getting put in there. Okay, so that's going to make it a whole lot easier to compare numbers when we're just looking at $1. So they wrote the equation, the initial amount, which we decided was going to be $1. And if you're thinking about this bank account, the bank account that we're looking at is the one that had 2% annual interest. So 2% is the same as 0.02. So it's getting compounded, that means it's growing. So we had to do 1 plus the 0.02 raised to the t for how many, it's just happening once a year. So there's our equation, 1.02 raised to the t. So we want to look at that though. Instead of compounding it once, we want to write a function equivalent to this that represents 12 compoundings per year, which is a power of 12t, instead of just compounding it once per year, which was the 1t. So the way that we're going to do this is by changing that 1 times t to 1 times 12 over 12. We haven't done anything. We all know that 12 over 12 is still 1. But 1 year is equal to 12 months. So we're converting from years to months here, excuse me. So when we do that, we have a power raised to a power. Well, when there's a power raised to a power, we can multiply. So they took that 1/12 and they just tore it apart from right here. They tore it apart and have the 1/12 inside the parentheses and the 12t outside of parentheses. And that's the same thing, because a power to a power, you multiply those things. So if you're working backwards, you can see how they're the same thing. So then they went ahead and calculated that. What is 1.02 raised to the 12th? Well, that's nothing more than 1.00165. So if we're going to think about that, what that amount is as a percentage, then roughly we're getting 0.165%. You move your decimal place over 2 places. You're getting 0.165% per month. That is slightly more than the 0.15% being offered by the SaveWell Bank. So the second local bank is the better choice. It appeared to be the better choice in the beginning. 2% appeared to be better than 0.15, but we had to check because you can't compare apples to oranges. You have to compare apples to apples. So that's what we did here. We converted this into looking at how much is compounding monthly in order to make 2% a month, or a year, to make 2% a month. That means that they're actually giving you 0.165% a month. And that is better than what the other local bank offered, which was 0.15% per month. For some reason, I cannot get that correct. So the thing to look out for is that you have to be careful that you're not trying to compare apples to oranges, that you put them in the same comparison category and then look at what they are. Look at both of them compounded each month or both of them compounded yearly. So part B says to do just that, compare the annual rates. So this time we want to write a function of the bank account that has the rate of 0.15%. We want to look at it compounded annually instead of monthly. And I cannot scroll with this. It's like jumping all over the place. Just stop for a minute here, Betsy. Okay, so let's look at this. So we put in our rate. 0.15% is the same as 0.001, and it's been compounded monthly. So right now, that monthly compounding, we want to look at that annually. So we know that annually is happening, instead of it happening, okay, let's just read this. Write an equivalent function that represents one compounding per year. And since there are 12 months in a year, the exponent then should be 1/12. So right now this represents 1 year. So we've got to change that. I said that backwards. Right now, this T represents, I'm sorry guys. Right now this T represents the fact that it's happening once a month. We want to look at it happening once per year. So we change our exponent to 1/12 T. If you really want to know what's going on in my head right now, I'm trying to teach this, but my kids are outside and they decided to give my dog a bath. So I just got done sweeping and mopping the house and cleaned everything with bleach water. And my kids keep coming in and out getting Dawn dishwashing liquid and towels. And I'm just imagining the dog coming back in. It's raining and muddy and nasty outside. And they're giving a dog a bath outside. So that's why I'm so distracted right now. So I'm sorry. That's where my mind is. Just thought I would share. Now we'll get back to math. So, back to this problem. The original function, and then we're going to compare it to this happening instead of once per year. We're going to look at, or we know that there are 12 months in a year. So we had to take that 12 and times it by 1/12. 12 times 1/12 is 12 over 12, which is 1. So we have not changed anything by rewriting it as 12 times 1/12. But what that allows us to do is then separate that, because back to our rules of exponent, a power raised to a power, we multiply. So that 12 that's outside there with that 0.0015, they're going to just take the 12 and put it here, and then put the 1/12 T out here. Because now remember, a power to a power, we multiply. 12 times 1/12 is still just 12 over 12, which is 1. So we're not changing the quantity, It's 1 times t, which is nothing more than just t. We didn't change this value of t that we had in this original problem up here. We're just writing it a different way so that we can compare the monthly amount to the yearly amount. They gave us the monthly. We want to look at it yearly, how much percentage that's going to be. So they go ahead and split that apart. Then they take that 1.0015, raise it to the 12th power, and they get 1.018. So if we move that over, we end up with 1.8% is our 1.81% is our annual compounding. The other bank offers 2% annually. So clearly the 2% is the better deal, but we didn't know that to begin with because, like I said, we cannot compare apples to oranges. We have to compare apples to apples. So it doesn't matter if you look at both of them monthly or if you look at both of them yearly, which is what we did in Part A. We looked at both of them yearly or monthly, and in Part B, we're looking at both of them. I'm confusing myself. In Part A, we looked at both of them monthly, and in Part B, we looked at both of them yearly and made our comparison. So we have your exit ticket here. I would like for you to try these problems once again. I'm going to go ahead and give you the answers because my concern isn't that you get the answer. My concern is that you learn how to do the problem. I want you to know the process. So you're going to find the approximate equivalent monthly interest rate if the annual rate is 3.4%. You're going to do this exactly like we just did the other one. This is the annual, so you're going to compare, you're going to change it to the equivalent monthly. And I'm going to go ahead and show you these answers. So I've jotted these down somewhere. You can hit pause and write down these answers and these problems, and I am interested in seeing your work. I want to see how you got these 3 problems. And that takes care of today's lesson. I hope you guys are having a good time, and I hope that my distractedness didn't distract you too much. Miss you guys.